Hi, Mustafa. If you'd like to introduce yourself, maybe a really quick introduction to the data availability problem, but just a short sort of focus on how you're solving it at Celestial, and yeah, how you've solved the problem or looked at the problem in your paper.
Sure, yeah. So by the way, I have to leave at past.
Sure.
But you guys can continue, obviously. So the data availability problem is basically trying to solve something called the data withholding attack. So for some context, when a block producer creates a block on a blockchain, they commit to a block header, not the actual data in that block. And that block header contains a commitment to that data, like usually the Merkle root of that data. And that, like, for example, in Bitcoin, you have a Merkle root of transactions, which is included in the block. But just because you have consensus over the Merkle root of the transactions doesn't mean that the miners or the block producers actually published the data behind those transactions. And this is a problem in the context of light clients. So it's not a problem for full nodes, because full nodes, they download all data themselves, so they wouldn't accept the block if they couldn't download the data. But it's more important for light clients because, and specifically light clients that use fraud proofs. So specifically, if you're a light client and you accept and you don't want to trust the block producers, then if the block producers submitted invalid transactions or created a block with an invalid transaction, then someone can send you a proof that some transaction in the block was invalid. But they can't do that if the data was withheld or was not published. So data availability is the problem of data availability basically asks, how can a light client actually verify that some data in the block was actually published to the network without the light client having to actually download all the data themselves to check that it was published? And you can kind of solve this with the concept of data availability sampling, which was described in the paper. Like the basic idea is that you apply an erasure coding scheme to the block data, so that if a block producer wants to hide just even a single byte or even a single transaction in the block, they have to actually hide, I believe, 75% of the block. They have to withhold 75% of the block. So that means that a light client can randomly sample different parts of the block, and the more they sample, the more likely they are to sample the 25% of the data that was withheld. And that means, assuming the block producer was doing this attack and the light client samples the part of data that was withheld, then they can easily detect that the data was not available because they wouldn't receive a response to the sample.
So you mentioned in the paper you're using this 2D encoding, but you mentioned it would, if you had a ZK proof that the encoding was correct, it may be optimal just to use 1D Reed-Solomon encoding.
Yeah, so the paper relies on fraud proofs to prove that erasure coding is incorrect. But you can use a 1D code for sure if you prove that erasure coding was correct in ZK. But there's many reasons why you don't want to use a 1D code. So for example, like the Ethereum danksharding scheme, it still uses a 2D code, even though they use KZG commitments to prove that erasure coding is correct. And one of the reasons for that is because it's very expensive to produce a 1D code with lots of data, in the sense that you can't parallelize it. where if it's a 2D code, you can parallelize the construction and repair of each row and column. Whereas like if it's a 1D row, if you wanted to repair any of the data, you have to download all the data.
Why? I think I lost my train of thought. So, shit. No, I was curious about because Ethereum uses validity proofs, the KCG stuff, and you guys are sticking to the fraud proofs. It sounds like,
Yeah.
and I'm curious. I assume that the fraud proofs will be generated by light clients. Am I right in that?
No, the fraud proofs are generated by like full nodes.
Okay, they're generated by full nodes, so they don't have to be computationally cheap. That was my kind of follow-up then. I was wondering how expensive is it to compute a fraud proof versus a validity proof of this?
Well, it's a lot cheaper to compute a fraud proof than it is to compute a ZK proof. Because computing a fraud proof is simply re-executing re-executing the computation of the code, which is just like pretty efficient. Like you can do like on our data as benchmarks, you can erase your code 4 gigabits of data per second. Whereas with ZK proofs, the main performance problems with KZGs is that it has extremely high computational overhead for computing the openings. I think like the latest benchmarks was like you need something like 200 to 300 machines to compute all the openings for like 100 for like I think it was a 32 megabyte block.
So that's why you're sticking with fraud proofs. Are there any other advantages to that approach over the Ethereum KCG one?
Yeah, so that's it's one of the reasons. So I kind of like I'm not entirely. So I mean, one of the main reasons why you might want to use KDGs. So I mean, I guess there's two main reasons why you might want to ZK prove the correctness of the visual code. Like the first reason is you want to eliminate like a challenge period. You want to eliminate like a challenge period to wait for a fraud proof, because that introduces a synchrony assumption. But the thing is, like, you still have a synchrony assumption because you still assume a synchrony assumption in the case where data is withheld, because you assume that the network is synchronous, so that in order for the light clients to share their samples with full nodes, so that they can reconstruct the data in a certain amount of time, assuming that some data was withheld. So, like ZK proving the correctness of the erasure code, you eliminate the need for fraud proofs, but you still have a synchrony assumption because you need to assume that within a certain time, the network will get together and reconstruct the entire block in case it's withheld. But the second reason why you might want to use KZGs is because if you might want to make it so that the block producers, in order to produce new blocks, they don't have to download all of the data in the previous blocks. They can also just sample the previous blocks. So in theory, that can reduce the download requirements for people running consensus nodes or block producers. But in practice, I don't think the performance improvements are as much as you would think they would be, because it reduces the download requirements, but it doesn't reduce the upload requirements, assuming the same number of consensus nodes, because the consensus nodes still have to re-upload the data to other nodes, like nodes that are sampling the data, in order to guarantee the data is actually available. So although it might decrease download requirements, it doesn't actually increase the upload requirements for the nodes.
I'm also curious if the existence of light nodes changes the trust assumptions on the full node network, in the sense that does it become 1 of n because you only need one full node to generate the fraud proof?
Yeah, in the case of the fraud proof based scheme, you only need one honest full node.
But for the general, like say the general Celestia network, you still have some like Byzantine 66% sort of thing.
Yes.
Yeah.
So the data availability assumption is that the data is available, as long as either 2/3 of the validators are honest, or if in case they're not honest, then data availability sampling scheme works. Like the data availability scheme, the data availability sampling scheme is only adding something in case that the validators are dishonest and they try to commit to a withheld block.
Hey, Mustafa, could you touch on adaptive attacks? Like what happens if the attacker, maybe they briefly make all of the data available and then they stop and withhold it, or maybe they make it available only to some light clients?
So the first thing you described is not really an attack, because it's fine. Like the purpose of data availability is not to make data permanently available. The purpose of data availability is to make sure that the data was published to the internet at least once by the block producer, so that anyone could have access, anyone could have downloaded it in a certain period of time. Like, and once anyone, let's assume like anyone have downloaded in this specific 30-day period, then it's those people's responsibility or network's responsibility to ensure the long-term storage of it. But in terms of the second attack you described, yeah, it's the case that the block producer could do like what's called a selective shared disclosure attack, where they only share, they can kind of like trick the first few light clients by only sharing enough data so that you can meet their sampling requests, but you don't release any more data than that to such that the network can reconstruct the erasure code. So like, let's say like you need 1,000 pieces to reconstruct the block, then you only release 999 pieces, such that you can like pass the sampling challenges of the first few light clients. So that is an attack you can do to kind of fool a minority of light clients. But you can kind of like get around that attack if you assume an enhanced network model where light clients are sending their requests through like a mixed network to kind of, so that the block producers or the full nodes can't link samples to specific light clients.
Mm-hmm. And in this model, are light clients really expected to store the responses they get so that they can participate in reconstruction?
So if they want to add security to the network, then they should store the samples so that that full nodes can download them from it in order to allow the block to be constructed. Because if they're not doing that, they're not really adding security to the network. They're kind of like checking the block is available, but they're not really adding security to the network because they're relying on other light clients to do that work. So yeah, they are expected to share their sampling requests with other nodes to allow the network to be constructed.
Okay, thanks. And then just thinking back to like, what if the first scenario I mentioned, like what if an attacker only makes the data available for such a short period that light clients don't have enough, or nodes don't have enough time to collect enough data to reconstruct the block? Then even with a mixnet, could that be used to fool some light clients that check it early, like the first few light clients?
So data availability sampling scheme relies on the assumption that there's some honest minority number of sampling light clients. So like let's just like it depends on your block size, but let's assume like for a certain block size, you need at least 1,000 honest light clients, that are sampling enough data so that the network can reconstruct it. And that's an assumption that needs to hold true. And part of that assumption is that light clients themselves are holding that data for a certain amount of time, like 30 days. If they're not holding it if they're not holding it for the correct amount of time, then that honest minority assumption kind of breaks. So it's not so much that you have to trust the block producer to hold it for a certain amount of time, is you have to trust the other light clients that are sampling to hold it for a certain amount of time.
But what I mean is, like, let's say it's a K of n erasure code, and let's say the attacker answers the first K-1 queries.
Yeah.
Then even with a mixnet, wouldn't that allow them to fool some light clients, maybe some of the first few light clients that do the sampling?
No, because the idea is like let's assume that you need let's assume that you need 1,000 pieces to reconstruct a block, but let's assume that you have enough light clients that they're actually making 2,000 sample requests. So what you'll want to do is those light clients will want to sample, they will want to send those requests of the network such that the full nodes cannot link any of those 2,000 requests to each other or to the light client. And so because they're anonymized, but they're also there's a random time delay in them, so that from a statistical perspective, those 2,000 shares as the sensitive network, they're completely random in terms of like what light clients or how they relate to each other. So what that means is like the very first sampling request and the very last sampling request, like the 2,000th one and the first one, could actually be from the same light client. So that means like if you only answer the first 1,000, you're not actually gonna fool any light clients, because all of those light clients, from a random perspective, they're all likely gonna have samples requests in the first 1,000 and the second 1,000 requests. Does that make sense?
Yeah, I think I get it now. I think adding random delays addresses the concern. Yeah, thank you.
I was also wondering in the paper how you determine the sort of safe probability thresholds to calculate minimum number of light clients required, and I think in the final section. Yeah.
Yeah. So in the paper we use a formula, because like basically the problem can be simplified to something called the coupon collectors problem, which kind of like asks well, just saying it, quoting it from Wikipedia, if each box of a brand of cereals contains a coupon, and there's n different types of coupons, what is the probability that more than t boxes need to be bought to collect all n coupons? You can think of the cereal boxes as light clients and the coupons as shares. So the question is like, how many like light clients you need doing certain sample requests do you need, such that they're all gonna cover all the shares, given that they don't coordinate with each other about what to sample. They all choose the random samples themselves. So it's mostly just like and so we use like this. So there's a formula in the paper that is used to calculate that. That's based on like Euler, a formula from Euler. But I mean, that's just one way of calculating it. You can also like calculate it through like a Monte Carlo simulation.
Yeah, but it's still a probabilistic.
Yeah, it's probabilistic.
Yeah, so that's what I meant. Where do you need to set that threshold, if you see what I mean?
What do you mean, like where? You mean percentage, like what percentage wise?
Mhm.
Or
Yeah.
so if you so in the that in the paper, there's a diagram that shows the relationship between how many light clients you have and how many light clients you have and the probability that they're all going to sample the chunk, all the samples together. And what you'll see is like it's on page 23. But what you'll see is like maybe I'll share my screen. A second. Okay, can you see my screen?
Not yet.
It says that you've started screen sharing, but that's all.
You can't see anything?
It's still loading.
Okay, I mean, it's usually screen sharing doesn't work for me anyway. But basically,
I can try if you want. I have the paper up.
yeah, well, yeah. So on page 23, there's a graph that shows that relationship. But basically, the gist is that once you get that one. So yeah, once you get to a certain number of light clients, there's no point in adding more. It's like a diminishing return.
Mhm.
It's like once you get to 99%, like there's no returns anymore.
Right. Yeah. Yeah. So it was the 99% I was curious about, right? Okay. Great. Thanks.
Well, yeah, exactly.
So you're using a two-dimensional scheme for this. Could you not theoretically do higher dimensional stuff and have a similar sort of, like, here it's proportional to something like the square root, like, you know, make the necessary shares to reconstruct the whole thing smaller by using higher dimensions?
Yeah, you could use higher dimensions, but there's extra overhead to having having higher dimensions. In the sense that, so if you with a 2D square, for n squared amount of data, you have to download n row roots. So it's like right now you have to download o square root n row roots. If you have a 3-dimensional square, then for n cubed data, you have to download n squared row roots. So you have to download that. There's higher overhead. So it only makes sense to use 3 dimensions if you have like a lot of data, like more than 100, like hundreds of megabytes of data per block, because then the overhead will be worth it. Because not only because if you use a 3D square, not only do you have to download the row and columns, you have to download the z-axis as well. It's like right now on the 2D, you have to download the roots on the x and y-axis. With a 3D one, you have to download all the rows on the there's a z-axis as well. So there's more overhead. There's more routes to download.
I guess you have to bounce soon. Also, very quick though, I think you mentioned that the nodes are not expected to save the data after 30 days. So is it expected that the network prunes and kind of its state doesn't grow over time?
Well, I mean, so yeah, I mean, in general, we expect the roll-up networks themselves, to have full nodes that archive data. In practice, like I would expect that at least someone is going to store the entire data, because there will still be a block size limit. So I'm sure like someone will store the data. But in kind of like in theory, we don't guarantee that. It's like we're only gonna like socially guarantee it for a certain number of days, but like people shouldn't expect to be able to like query the network a year later or something like that, or like 10 years later. And and retrieve historical data that no one cares about, for example.
Yeah, I think that makes sense. So if rollups use something like a longest chain sort of style consensus, then after 30 days, like, you know, breaking that up will be a big hassle.
Well, I mean, like rollups also technically you don't need historical data for like rollups either, unless you want to sync the chain from scratch. Like technically, if you want to like bootstrap a new node, you only need to get the latest state of the chain. That you don't really need the historical transactions unless you want to like reconstruct the state from scratch.
Yeah.
Okay, do we have any last questions from Mustafa?
Yeah, feel free to drop me an email or something if you have any more questions.
Yeah. I noticed that you used write some code. That's a very classical erasure code scheme. But I'm wondering why RS code? I mean, there are plenty of other choices, right?
Well, so first of all, like, it can't be a fountain code. Like, it has to be. So you mean like what kind of other codes do you mean? Like, do you mean like a rateless fountain code?
Yeah. Let's take fountain codes as an example.
Yeah. So like for example, like you can't use a rateless fountain code because you can't authenticate like with the fountain code. You can generate unlimited number of new chunks, but you can't authenticate those chunks to the block producer. But there needs to be a way for the block producer to commit to the specific chunks, so that you can like you need to know like the fountain code. Like if someone gives you a chunk, you don't actually know that that chunk was actually generated correctly from the original data. I think there's some ZK way of there's like a paper from like 10 years ago that proposed like a zero knowledge way of doing it using like a morphic cryptography or something like that, but the performance was very slow. So that's why we have to use Reed-Solomon codes, not Reed-Solomon code specifically, but similar codes to that. But specifically, we use Reed-Solomon code because it seems to be the most widely adopted, and also there's libraries out there that are very hardware optimized to have very fast encoding rates.
Okay. Yeah. Do you remember which paper mentions the performance of the with FHE and fountain code?
Let me see if I can find it.
Well, thank you.
Let me quickly Google it. Yeah, I'll link to it here.
Okay. Yep. Cool. Thank you very much.
All right, and well, thanks everyone.
Thanks
Yeah,
very
feel
much
free
for
to
your
email
time.
me. Cheers.
Thank you.
Thanks a lot.
Bye.
Thanks a lot.